aliens exist? There are a few questions of more profound importance when it comes to our place in the universe. It cuts to the heart of something deeply human, this compulsion to look up at the night sky and wonder whether anything is looking back. But while the majority of people believe alien life is out there somewhere among the hundreds of billions of stars in our galaxy, it's a lot harder to pinpoint exactly where we should be searching. At least, that was the case, until we started looking at the TRAPPIST-1 star system. In the hunt for alien life, there are few better candidates anywhere in the known cosmos. We know that Earth-like planets are fertile ground for life, rocky worlds with stable surfaces, orbiting at just the right distance from their star to allow liquid water to pool and persist. After all, life arose here on one such world, and it did so with remarkable speed once conditions allowed. So, to find a planetary system that is seemingly full of Earth-like planets and is relatively close by in cosmic terms at just 40 light-years from our own sun, it's no wonder that scientists are captivated. Those researchers have now turned humanity's most powerful space telescope, the James Webb Space Telescope, on the TRAPPIST-1 system, training its extraordinary infrared instruments on worlds that previous generations of astronomers could only dream of studying up close. So, it's time to find out what it has seen and what it means. Has Webb confirmed that the planets of the TRAPPIST-1 system are truly conducive to life? Or does the data send us back to the drawing board, searching once again for somewhere else to place our hopes? Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now, and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. Evaluating a star system for compatibility with life is a genuinely complex undertaking. Although much of the assessment comes down to the nature of the planets themselves, a large portion of the conditions that determine habitability depend on the star those planets are orbiting. So, let's begin at the heart of the TRAPPIST system, with TRAPPIST-1 itself, the ultra-cool red dwarf star sitting at the center of one of the most fascinating planetary systems ever discovered. It is a star only a little bigger than Jupiter in terms of physical size, yet considerably more massive, packing far more material into a comparatively compact sphere. Red dwarf stars are the most common type of star in the galaxy by a significant margin. Even our nearest stellar neighbor, Proxima Centauri, is a red dwarf, and so are roughly 50 of the closest 60 stars to our own solar system. Being so cool and dim means these stars burn through their fuel at an extraordinarily slow rate, making them exceptionally long-lived. Stellar models suggest red dwarfs could persist for trillions of years, timescales that dwarf the current age of the universe itself, which sits at just under 14 billion years. Despite their abundance and longevity, red dwarfs are typically considered dubious candidates for hosting life. The core problem lies in the geometry of their habitable zones. The Goldilocks zone, meaning the range of distances from a star where temperatures could allow liquid water to pool on a planet's surface, sits extremely close to a red dwarf because the star emits so little heat. Any planet orbiting within that zone is likely to become tidally locked, meaning the same hemisphere always faces the star, while the other remains in permanent darkness. The day side would be perpetually bathed in stellar radiation, while the night side would grow cold enough for atmospheric gases to freeze out entirely, potentially stripping the planet of the very blanket of air it needs to retain warmth and support chemistry. Red dwarfs also tend to be volatile in another way. Many are classified as flare stars, capable of erupting with sudden, dramatic increases in brightness that can temporarily outshine their normal output by enormous factors. These events are broadly similar to solar flares on our own sun, but scaled up considerably. The bursts of high-energy radiation that accompany such flares can be deeply hostile to the development of life and can erode or even strip away the atmospheres of nearby planets during particularly intense events. TRAPPIST-1, however, stands apart from many of its red dwarf relatives in this respect. It flares at a rate roughly 30 times lower than a typical red dwarf star, a characteristic that significantly improves the odds that its planets have managed to hold on to their atmospheres over geological timescales, and that conditions on their surfaces may be at least somewhat more stable than those endured by planets around more temperamental stars. Although TRAPPIST-1 was first detected in 1999, its full planetary lineup wasn't revealed until 2017, when it became the first and only planetary system to be discovered using the TRAPPIST optical robotic telescope. That instrument consists of two components working in tandem: TRAPPIST South, situated in the mountains of Chile, and TRAPPIST North, positioned in Morocco's Atlas Mountains. Both telescopes use a technique called transit photometry, which works by precisely measuring periodic dips in the brightness of a star. When a planet passes between us and its host star, it blocks a small fraction of the star's light, producing a measurable and repeatable dimming signal. By accumulating many such observations over time, astronomers were able to isolate the individual orbital signatures of multiple planets moving around TRAPPIST-1. Initial analysis of the data revealed only the 3 innermost planets. But as observations continued, combining data from both TRAPPIST telescopes with additional measurements from the Spitzer Infrared Space Telescope, that total climbed to 7. More remarkably still, all 7 planets are rocky and all are at least roughly Earth-sized in their dimensions, making TRAPPIST-1 the record holder for the most Earth-like planets found orbiting any single star. With such a small and dim star at the center of the system, though, the question of whether any of these worlds could genuinely be habitable remains very much open. Our current observations, it should be said, are far from complete. The picture we have today will only sharpen and improve as new data comes in. But what follows reflects our best understanding at this point in time. Viewed optimistically, 6 of the 7 planets in the TRAPPIST-1 system orbit within or near the system's Goldilocks zone. These worlds are packed remarkably close together and close to their star, such that even the outermost planet orbits at a distance of only about 9 million kilometers from TRAPPIST-1. For context, Mercury, the innermost planet in our own solar system, orbits the Sun at roughly 58 million kilometers. TRAPPIST-1b is the closest planet to the star, and it moves with corresponding speed. A full year on TRAPPIST-1b lasts only 36 hours. It is slightly larger than Earth in physical size, but carries roughly the same mass, which means surface gravity there would be approximately 80% of what we experience here, a figure comparable to conditions on Venus. Early analysis suggested it might resemble Venus in other ways too, with a thick, dense atmosphere potentially rich in carbon dioxide that, combined with its proximity of just 1.7 million kilometers to its star, would have made the surface extremely hot. However, more recent observations from the James Webb Space Telescope appear to have revised that picture considerably, offering new and more nuanced clues about what this world might actually be like. The James Webb Space Telescope is one of the most powerful and sensitive telescopes ever built, and the teams who played a central role in developing it were rewarded with guaranteed observation time as part of that recognition. One group, known as the Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy, the DREAMS team, immediately wanted to set James Webb's sights on the TRAPPIST-1 system, a collection of rocky worlds that had tantalized astronomers since its discovery. The James Webb Telescope is uniquely sensitive and precise, so much so that it can detect spectral signatures from the thin band of gas that makes up the atmospheres of these planets, located a whole 40 light-years from our own solar system. To put that in perspective, it is essentially reading the chemical fingerprint of an atmosphere thinner than a coat of paint, wrapped around a world across an almost incomprehensible distance. It achieves this remarkable feat through a technique called transmission spectroscopy. As an exoplanet passes in front of its host star, James Webb does not simply measure the drop in brightness caused by the planet blocking some of the starlight. It also analyzes how the spectrum of that light changes as it filters through the planet's atmosphere on its way to us. The telescope's near-infrared spectrometer, or NIRSpec, measures the wavelengths of infrared radiation closest to the visible spectrum. Molecular bonds absorb energy in this particular range, and different bonds absorb different wavelengths with remarkable specificity. The carbon-hydrogen bond, found in methane, for instance, leaves a distinct mark at one set of wavelengths, while the carbon-oxygen double bond in carbon dioxide leaves its own unique signature elsewhere. This means that by carefully measuring which wavelengths are absorbed as a planet transits its star, scientists can first determine whether an atmosphere exists at all, and then, if one does, identify precisely which gases are present within it. Getting clear readings from the TRAPPIST-1 system has actually proven easier than expected. The data gathered is roughly 10 times more sensitive than what scientists have on any comparable planetary system. The reason for this is somewhat counterintuitive. It is because the star itself is relatively dim. When a planet passes in front of a faint star, the light it blocks causes a proportionally larger drop in apparent brightness than the same planet would produce transiting a large, luminous star. A bigger difference in brightness is simply easier to measure with precision, and TRAPPIST-1's modest glow works very much in astronomers' favor. With the help of Webb's data, spotting and analyzing atmospheres in the TRAPPIST-1 system began to feel less like a long, grinding slog, and more like a compelling puzzle, with scientists spending time every day trying to crack the code on which of these worlds might be capable of supporting life. Thanks to the James Webb Space Telescope, it has been revealed that TRAPPIST-1b runs considerably cooler than models had predicted, with surface temperatures on its star-facing side reaching only around 227 degrees Celsius. That measurement, while still scorching by any human standard, is low enough to essentially rule out any significant atmosphere. If one existed, it would be trapping far more heat. There is no realistic prospect of life on this bare, airless rock. But what of the other planets in the system? TRAPPIST-1c is the next planet outward, orbiting at a distance of around 2.4 million kilometers from its star, completing one full year in just 58 hours. At this orbital distance, it receives approximately twice the amount of starlight that Earth receives from the Sun. Its size and mass are each roughly 10% greater than Earth's, which translates to a surface gravity very similar to what we experience here. Like its inner neighbor, scientists initially suspected TRAPPIST-1c might host a thick water vapor atmosphere. Once again, however, James Webb told a different story. The telescope revealed a surface temperature cooler than expected. In fact, the coolest ever recorded for a rocky exoplanet based on thermal readings alone. This means that TRAPPIST-1c either has no atmosphere whatsoever, or one composed of carbon dioxide so thin it would make the already sparse Martian atmosphere seem dense, with no clouds to speak of. The most likely explanation is that this planet simply formed with very little water to begin with, since at these temperatures, any water present would readily become vapor and show up in the atmospheric readings. And scientists are not detecting any. Next is TRAPPIST-1d, sitting only about 1 million kilometers further out than TRAPPIST-1c, a gap that sounds modest, but places it in meaningfully different thermal territory. A year here lasts just 97 hours. TRAPPIST-1d is something of a hybrid between Earth and Mars in terms of its physical character. It is about 30% smaller than Earth and carries only 30% of Earth's mass, giving it a surface gravity just under half of what we feel on our own planet. Crucially, it sits on the inner edge of the so-called habitable zone, sometimes called the Goldilocks zone, the orbital band where surface temperatures are in principle cool enough for liquid water to pool and persist on the ground. It receives only about 4% more starlight than Earth does, though this is further complicated by periodic solar flares from its host star, meaning surface conditions are likely still quite harsh compared to what life as we know it would prefer. According to data from the James Webb Space Telescope, TRAPPIST-1d does not appear to have an Earth-like atmosphere. No water vapor, methane, or carbon dioxide have so far been detected. However, that does not rule out every possible scenario. There are some intriguing indications that the planet could harbor a volatile layer at its surface, perhaps even a liquid ocean, concealed beneath a thick, optically obscuring atmosphere that might be confounding Webb's readings and preventing a clean atmospheric fingerprint from emerging. This is where the interplay between oceans and atmospheres becomes critically important. As mentioned, all of the TRAPPIST-1 planets are tidally locked to their star, meaning one hemisphere is in perpetual daylight and the other in endless night. A thin or absent atmosphere would allow one side to be scorched relentlessly, while the other freezes in permanent darkness, much like the situation on Mercury. Venus, by contrast, demonstrates the alternative. Its dense atmosphere circulates heat so effectively around the planet that temperatures remain almost uniform, whether you are standing in full sunlight or on the dark side. A powerful reminder that atmosphere is everything when it comes to the survivability of a world. So, if TRAPPIST-1d has only a thin atmosphere or small ocean, the chances are that one side of the planet would be devoid of anything but bare, lifeless rock, while the other side might be buried under vast sheets of ice. There might be a narrow band of habitability threading through the twilight zone where permanent day meets permanent night, but that would essentially be the extent of it. With a large ocean or a sufficiently thick atmosphere, however, the planet might be able to circulate and distribute heat far more effectively, meaning it could potentially be habitable across much of its surface, at least as far as we understand what habitability actually requires. This planet may well turn out to be an ocean world, one holding over 250 times the amount of water contained in all of Earth's oceans combined, though other studies have raised the possibility that its atmosphere could bear a much closer resemblance to that of Venus. And then there is the starker possibility at the other end of the spectrum. There could be no atmosphere there whatsoever. The James Webb Space Telescope has not been able to rule this out in either direction, leaving TRAPPIST-1d frustratingly ambiguous for now. Moving further out, TRAPPIST-1f sits at an orbital distance of 5.8 million kilometers from the star, completing a full year in just 220 hours, or roughly 9 days. We are still technically within the Goldilocks zone here, but the warmth of the star is beginning to thin noticeably at this distance, and conditions are growing considerably cooler. The planet itself is reassuringly Earth-like in terms of size, though it is noticeably less dense, which means surface gravity would clock in at around 80% of what we experience here on Earth. The most recent studies of TRAPPIST-1F have pointed to that lower density as an important clue, suggesting the planet is likely composed of around 20% water by mass. At this particular distance from the star, that enormous quantity of water would not sit quietly in oceans or ice sheets. Instead, the water would drive a powerful greenhouse effect, trapping heat and pushing temperatures to extremes that would keep water locked in a gaseous state rather than a liquid one. This kind of world has earned itself a vivid name in planetary science, a steam world. And despite the presence of so much water, it would probably be no more welcoming to life, as we know it, than the ice giants or gas giants of our own solar system, owing to the crushing atmospheric pressure and surface temperatures likely running into the hundreds of degrees Celsius. TRAPPIST-1G is slightly larger than Earth and orbiting at around 7 million kilometers from the star and completing each circuit in approximately 12 days. Detailed data on this planet remains relatively sparse compared to some of its neighbors, but water has again been identified as a component of the world. It still sits within the Goldilocks zone, though right at its outermost edge, which means it just barely holds on to its status as a candidate for potential habitability. And then there is TRAPPIST-1H, the outermost of the known planets in this system. It orbits at 9.3 million kilometers from the star, taking 19 days to complete each lap. It is the smallest of all the identified exoplanets here, and also the least dense, giving it a surface gravity comparable to that of our own moon. Being this far from an already cool red dwarf star means the planet is almost certainly icy, as the water it does possess would likely be permanently frozen. Theoretically, if TRAPPIST-1H happened to have a hydrogen-rich atmosphere capable of acting as a potent greenhouse gas, liquid water on the surface could become a possibility. But very little is currently known about this outermost world, and that remains firmly in the realm of speculation. So, we have now traveled the full breadth of the TRAPPIST-1 system. Could any part of it genuinely be habitable? The honest answer is that it depends on a number of factors, and the picture is genuinely mixed. Some of these worlds look increasingly unlikely, while others have so far refused to be ruled out. Water has been detected on more than one of them. The host star is a red dwarf, yes, but it is a relatively quiet and well-behaved one by the standards of its class. If these planets possess magnetic fields strong enough to deflect the worst of the stellar wind, that removes one of the most significant threats to long-term atmospheric survival. They are also all broadly Earth-sized, with comparable gravities and densities, which is not in itself a guarantee of anything, but we do have one compelling proof of concept for that combination supporting life. And although tidal locking is a genuine complicating factor, these planets may still have atmospheric or oceanic mechanisms capable of redistributing heat across their surfaces more evenly than a worst-case scenario would suggest. But there is one planet from this lineup that deserves its own moment in the spotlight, because if you were paying close attention, you may have noticed that something was skipped over. The journey went from TRAPPIST-1D directly to TRAPPIST-1F, bypassing a letter entirely. That was deliberate because the most compelling candidate of all has been held back until now. TRAPPIST-1E. This planet orbits at just 1/13 of Mercury's orbital distance from the Sun, and that tight, seemingly claustrophobic path puts it right at the heart of the predicted habitable zone, the sweet spot where conditions for liquid water on a surface are considered most plausible. At this distance, TRAPPIST-1E receives roughly 2/3 of the energy that Earth receives from the Sun, a difference that is meaningful but far from disqualifying, and it is precisely this positioning that has made the scientific community so eager to study it more closely. Using measurements from the James Webb Space Telescope, researchers have already been able to discount TRAPPIST-1C and TRAPPIST-1D as likely candidates for having meaningful atmospheres. But the data coming back from observations of TRAPPIST-1E, a rocky planet measuring around 0.9 times the size of Earth, told a different and far more intriguing story. The results hinted that this planet may in fact possess an atmosphere, and that possibility was more than sufficient motivation for the DREAM science team to commit their entire allocation of guaranteed James Webb Space Telescope observing time to investigating it further. So far, they have captured 4 separate transits of TRAPPIST-1E, with James Webb patiently building up a picture of a world that may yet have something remarkable to reveal. But what did they find? Well, we can start by discounting a few possibilities. We now know that TRAPPIST-1E does not have a primordial atmosphere. The kind of atmosphere a planet is born with, inherited from the swirling cloud of gas and dust from which it originally formed. These primordial atmospheres are usually dominated by light gases like helium and hydrogen, and neither has been detected around TRAPPIST-1e. They were almost certainly stripped away by the star's intense radiation early on in its life, before the planet ever had a chance to settle into anything resembling stability. Nor does TRAPPIST-1e appear to have a carbon dioxide-dominant atmosphere like Venus, which is famously thick and dense, trapping heat so effectively that its surface temperatures exceed those of Mercury, despite being farther from the Sun. An atmosphere more like that of Mars, thin, sparse, and offering little in the way of protection or insulation, also seems unlikely given the most recent measurements. And believe it or not, all of this turns out to be good news. None of those types of atmospheres could plausibly support life, at least not as we understand it. So, what kind of atmosphere might it actually have? Here's the big one. There could be an Earth-like atmosphere, one dominated by a heavier gas, such as nitrogen, combined with a meaningful greenhouse effect driven by water vapor, carbon dioxide, or methane. Such an atmosphere, with a surface pressure of around 1 bar, equivalent to what we experience standing on Earth, may be able to sustain enough heat transfer across to the dark side of the planet to allow for a global surface ocean, even accounting for the fact that TRAPPIST-1e is tidally locked, and one face of it never sees daylight. Were that confirmed by future observations, it would make headlines across the world and fundamentally reshape how we think about life in the universe. However, that might be too much to ask of the current data. The measurements instead slightly favor the idea that TRAPPIST-1e is a cold planet without a global ocean covering its surface. What may be happening instead is that high levels of methane in the atmosphere are creating a reverse greenhouse effect, sometimes called an anti-greenhouse effect. TRAPPIST-1 has a surface temperature of around 2300 degrees Celsius, considerably cooler than our own sun's, roughly 5500 degrees Celsius. And as a result, more of the energy it outputs is shifted toward near-infrared wavelengths. Atmospheric methane is particularly good at absorbing energy at those wavelengths before it even reaches the planet's surface, and then re-emitting that energy back out into space. The net result is a cooler atmosphere than you might otherwise expect. For a tidally locked world like TRAPPIST-1e, this would mean that liquid water might only exist on the sunward face, the hemisphere that permanently faces the star. No global ocean in that scenario. But that is not necessarily bad news for the prospects of life. Such conditions could actually satisfy what Charles Darwin called the warm little pond hypothesis. The idea that life could have originated in small, shallow bodies of warm water, rich in chemical ingredients, where the right reactions could repeat themselves over and over across geological timescales. Atmospheric modeling has backed this up in encouraging ways. Computer simulations suggest that even if TRAPPIST-1e has only limited surface water, or if much of that water is locked away on the permanently dark side of the planet, it could still maintain a stable atmosphere over long periods of time. Though this might lead to what researchers describe as Terminator habitability, a scenario where life could only find a foothold along the dynamic boundary between the day and night sides of the planet. A band of perpetual twilight, where temperatures might be just right and the environment sufficiently stable for complex chemistry to take hold. But surface water is not the only avenue worth considering. We know TRAPPIST-1e is a rocky world, but beyond that, its internal structure remains largely a mystery. It may be an icy volcanic planet with a liquid ocean hidden beneath a frozen crust, much like what we find on Europa, one of Jupiter's moons, or Enceladus orbiting Saturn, both of which are considered serious candidates in the search for life within our own solar system. Some researchers believe life on Earth may have first emerged near deep-sea hydrothermal vents, where chemical energy and heat from the planet's interior provided the necessary ingredients, and the same process could in principle unfold on TRAPPIST-1e. No matter where on the planet water might be found, life remains a genuine possibility. There is an available energy source, and potentially an atmosphere that provides the chemical building blocks life needs to get started. But there is one significant issue that scientists cannot ignore. Although all of these scenarios are physically plausible, researchers cannot completely rule out the possibility that TRAPPIST-1e is simply a cold, barren, and airless rock, a marble floating in space with no atmosphere whatsoever. So, we need to talk about what could prevent a stable atmosphere from ever forming in the first place. And the answer, in this case, points directly back to TRAPPIST-1 itself. Now, I mentioned earlier that TRAPPIST-1 is not as hostile as some other red dwarf stars. But that is an admittedly low bar to clear. Let's take a much closer look at what this star is actually like. Imagine standing on the surface of TRAPPIST-1e for just a moment. Look up. The star above you would appear more than 4 times as large as our sun looks from Earth, an enormous brooding presence filling the sky. It would glow a deep red-orange, bathing everything in a light that resembles a perpetual sunset at the end of a long summer day. It would be a genuinely extraordinary sight, but that beauty comes with real danger. Red dwarfs are extraordinarily active stars, and they produce stellar flares that are not only more powerful than those our sun generates, but far more frequent. The worst geomagnetic storm ever recorded in human history was the Carrington event of 1859. A catastrophic solar outburst so powerful that it caused telegraph systems across North America and Europe to fail, and auroras were seen as far south as the Caribbean. By most estimates, it was a greater than 1 in a 100-year event for our sun. TRAPPIST-1 is believed to unleash a flare of comparable intensity more than once every 2 days. Standing on TRAPPIST-1e, you would likely be able to watch solar flares arcing dramatically out into space in real time. A spectacular and terrifying reminder of just how violent this little star can be. And they carry huge amounts of energy toward a planet, enough that, over time, any atmosphere could be stripped away entirely, making life, as we know it all, but impossible. That's assuming the atmosphere was ever allowed to form in the first place. As mentioned, red dwarfs are stupendously long-lived. TRAPPIST-1 is expected to exist for 10 trillion more years. That is 700 times the current age of the universe. By comparison, our sun likely has only 5 billion years remaining before it swells into a red giant and engulfs the inner solar system. You might think that given the remarkable stability and extraordinary lifespan of a red dwarf, there would be more than enough time for life to find a way. But because of their long lives, their chaotic and energetic teenage years, that turbulent period before red dwarf stars finally settle into a quieter routine, are correspondingly longer and more punishing. It is during these formative years that some planets begin to generate their own atmosphere, slowly shedding their primordial hydrogen and helium envelope and replacing it with one comprised of heavier molecular gases, such as carbon dioxide, nitrogen, and methane. These chemicals are gradually released from deep inside the planet through sustained volcanic activity, essentially exhaled from the world's interior over millions of years. The problem is that if the aggressive atmosphere stripping phase of a star persists for too long, an Earth-sized planet may simply not have enough geological resources within its interior to fully generate a stable, life-supporting secondary atmosphere before its window closes. The unfortunate reality is that if a planet's atmosphere isn't firmly established within about 5 billion years, it may never generate one at all, condemning the planet to a kind of death sentence before it was ever truly permitted to live. So, is TRAPPIST-1e actually habitable? It is admittedly starting to sound rather hopeless for TRAPPIST-1e, and it is a fair question to ask how this world remains one of the most promising candidates we know of. But the honest answer is that we simply do not know yet, one way or the other, whether a meaningful atmosphere has survived. And as we have already seen, there are genuine hints pointing toward its existence. Furthermore, although the star's violent outbursts may ultimately prove to be TRAPPIST-1e's downfall, those same outbursts may also be completely necessary for life to have begun in the first place. UV radiation unleashed by stellar flares may actually be essential to the synthesis of RNA building blocks, molecules that sit at the very heart of the metabolism of every living organism ever discovered on Earth. Life, it seems, may owe its origins to the same destructive energy that threatens to extinguish it. And now that TRAPPIST-1 has entered its calmer main sequence phase, with significantly lower UV and X-ray irradiation than during its volatile juvenile past, there is a genuine possibility that a stable, habitable atmosphere could persist on TRAPPIST-1e today. Such an atmosphere could also find protection from the star's continuing flares through the planet's own magnetic field, much in the same way that Earth's magnetic field deflects the relentless stream of charged particles emanating from our sun. Earth's magnetic field exists because its outer core is a vast, churning mass of molten iron and nickel, whose motion generates a powerful electromagnetic shield around the planet. There is good reason to believe that TRAPPIST-1e could possess a remarkably similar system. In fact, TRAPPIST-1e's close orbital proximity to its red dwarf host could actively help sustain that magnetic field rather than undermine it. If TRAPPIST-1e follows a slightly eccentric orbit, the gravitational pull of the star would repeatedly compress and then relax the planet's physical shape as it traces its path. A constant, rhythmic squeezing. This process generates internal friction deep within the planet, and that friction produces heat, potentially warming the interior by as much as 0.18 watts per square meter. To put that into perspective, that is roughly 24 times the tidal heating flux generated inside the Earth. enough to keep the interior active, molten, and magnetically alive. We see a similar process playing out on Jupiter's moon, Io. Io is tidally locked and follows an eccentric orbit, meaning it gets continuously stretched and squashed by the gravitational tug-of-war between Jupiter and the other large Jovian moons. This relentless kneading pumps enormous amounts of energy into the moon's interior, making Io the most volcanically active body in the entire solar system, a world of perpetual eruption and resurfacing on a scale nothing else we know can match. So, where does all of this leave us when it comes to TRAPPIST-1e? We may be looking at an Earth-sized, volcanically active rocky planet that possesses the chemical building blocks for life, its own atmosphere, and a protective magnetic field, all while orbiting comfortably within the habitable zone of a relatively calm red dwarf star. That would be a remarkable thing, or it could turn out to be a cold, dead world that never quite made it. The honest answer is that we simply don't know yet, and the debate among scientists remains very much alive. We may not get a definitive answer until the proposed Habitable Worlds Observatory comes online, a next-generation telescope being designed specifically to search for signs of life around stars, like our own sun, with a planned launch window around 2041. Until that instrument exists, the James Webb Space Telescope represents our best and most powerful tool for probing these distant worlds, and it's worth pausing to appreciate just how extraordinary that is. The fact that we can measure the light absorbed by a thin gaseous layer wrapped around a rocky planet, orbiting a dim red dwarf star 40 light-years away, is a genuinely stunning achievement of human ingenuity. Scientists have not given up hope, and they haven't stood still either. They've studied the first rounds of James Webb data carefully, identified the limitations in their methods, and refined their techniques to achieve more precise and reliable measurements. As more Webb observations are analyzed, researchers hope to confirm or rule out the presence of carbon dioxide and a stable secondary atmosphere, both of which would represent a crucial milestone in the search for life on TRAPPIST-1e. There hasn't been a breakthrough on that front just yet. The most recent study on the subject tentatively points toward the possibility that TRAPPIST-1e might host a methane atmosphere. But even that tantalizing hint comes with a significant caveat. The signal could be interference from the star itself, with methane present in TRAPPIST-1's own atmosphere getting in the way and mimicking what a planetary atmosphere might look like. Disentangling the planet's signal from the stars is one of the central technical challenges researchers are working to overcome. Perhaps TRAPPIST-1e and its neighboring worlds will turn out to have atmospheres that are unique and deeply inhospitable to anything we would recognize as life. Perhaps they'll have conditions that could, in theory, support it. Or maybe, just maybe, we'll find something that feels startlingly familiar, a world that mirrors our own in some profound way. There is something genuinely exciting about finding this much potential for life relatively close to home, even nestled within such an extreme and challenging environment. The search continues, and every new observation brings us a little closer to an answer. But whatever the atmosphere turns out to be on TRAPPIST-1e, with the recent discovery of formations on Mars that are thought to have been impossible to form without the presence of life, I find it increasingly hard to shake the feeling that the discovery of extraterrestrial life feels not just possible, but inevitable. The universe is simply too vast, too ancient, and too chemically rich for Earth to be the sole experiment in complexity and consciousness. Every time we look a little closer, whether at the frozen subsurface of Europa, the methane cycles of Titan, or the spectral fingerprints of distant exoplanet atmospheres, we find conditions that edge closer to familiar. The question is no longer really whether life exists beyond our pale blue dot. The only question is when we will finally find it. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.